Welcome to Brain Vision.
In this situation, we have a compass needle that is pointing 28 degrees east of north. So theta 1, we're going to say, is equal to 28 degrees. But when it moves 12 centimeters to the east of the vertical, we're now inside of a building next to a wire. So R is 12 centimeters or 0.12 meters. And the angle it now points is 55 degrees east of north. So theta 2 is 55 degrees. The magnetic field of Earth is 0.5 times 10 to the minus 4 Tesla, or 5 times 10 to the minus 5 Tesla, however you prefer to write it. And we're asked to find the current in the wire. So the first thing I'm going to do is I'm going to write out the vector for the magnetic field of Earth, as well as the magnetic field of the wire. So B sub E is going to be equal to B. The x component is the sine of theta 1. The reason it's the sine of theta 1 is based on the way that we defined theta to be. So we defined theta to be east of north. If we had asked for the north of west direction, then it would have been 90 minus 28 degrees, and you could have used the cosine of that angle. But we used the east of north angle, and so we're going to use the sine of that for the x component, or in other words, the I hat component. And this is going to get, and I forgot to write B sub E. I just wrote B. So this is the magnitude of Earth. So this is B sub E. Okay, and then the y component is going to be B sub E times the cosine of the angle theta 1. In the in the y hat or j hat direction. The magnetic field from the wire, that vector, B sub W, is going to be equal to B sub W times the sine of the angle, this time theta 2, in the I hat direction, plus B sub W times the cosine of the angle, theta 2, in the j hat direction. So I'm going to break this into its vertical and horizontal components here. So the magnitude of the total magnetic field, we'll just call that B. That's from the wire and from Earth. So that times the sine of the angle theta 2 is going to just be equal to the magnetic field from the Earth. This is B sub E times the sine of the angle theta 2. This is because there is only a horizontal direction from Earth. But the vertical direction is going to come from Earth and the wire. So here, B times the cosine of the angle theta 2 is going to be equal to B sub E times the cosine of the angle theta 1 minus B sub W. So again, because the entire magnetic field is just in the vertical direction, B sub W times the cosine of the angle is just B sub W, because the angle here would be 0. So the cosine of that angle is just 1. Okay, so now we can divide the top and the bottom of equation by one another to solve for B sub W. So B times the sine of the angle theta 2 divided by B times the cosine of the angle theta 2. Well, first we can just go ahead and simplify that, because there's a B on the top and bottom. So those B's cancel, and the sine of an angle divided by the cosine of the angle is equal to the tangent of the angle. So this is the tangent of the angle theta 2. Okay, but what was B sine theta 2? It was equal to BE times the sine of the angle theta 2. Okay. And this is divided by B cosine of theta 2, which was BE times so this was supposed to be divided by cosine of theta 1. So this is theta 1. Sorry about that little typo there. B cosine theta 1. This should be theta 1 down here. Okay. Oh, no, I was right. It's theta 2. Sorry about that. Of course it's theta 2. That's how we get that tangent of the angle theta 2. So this would be B times the cosine of the angle theta 1 minus B sub W. So we can just rearrange this equation to solve for B sub W. We ran out of room here, but we'll do it on another page. And we find that B sub W is equal to B sub E, which we know, times the cosine of the angle theta 1, which we also know, minus b sub e, which we know, times the sine of the angle theta 1, which we also know, divided by the tangent of the angle theta 2, which we also know. So we can just plug all of our values into this expression, and we find that b sub w is equal to 2.77 times 10 to the minus 5 Tesla. Okay, using that information, we can find the current in the wire because b sub w, by definition, is equal to mu naught, the magnetic permeability of free space. That's 4 pi times 10 to the minus 7 newtons per ampere. If you want to look that up, you can find more information about it. Multiplied by the current I in the wire, that's what we're trying to find. We'll call that I sub w, divided by 2 times pi times r, which we were given. So we can just rearrange this to solve for I sub w. And we find that I sub w is equal to 2 pi r times b sub w divided by mu naught. Plugging in those values into this expression, we find that I sub w is 16.6 amperes. So 16, let's redraw that 6 to make it look a little nicer. 16.6 amperes. And then it also wants to know directionality, but using the right-hand rule, the directionality would have to be downward. So we can box that in as our solution to the question.